Hey guys, welcome to System Design Fight Club. I'm going to cover chapter 2 of Alex Shu's new upcoming book, Machine Learning System Design. This one is Visual Search System. I'm going off of just the titles. This is my prediction for what's going to be in this chapter. The book just is releasing on February 1st. This video is the last one that I'm doing in the series. It was actually kind of seemed like the trickiest one. It involves machine learning on images, which is I have a lot less experience with that. So it seemed like this one was one of the trickiest for at least me. So that's why I did this one last. It should be a really interesting problem. These are some of the resources I've used for trying to figure out how to do this problem. It was like I said, quite a bit of a challenge. It looked like it was probably going to be item-based collaborative filtering, but I'm not sure if that's quite the way that I went with it. I think for my first approach, you can probably really call it item-item collaborative filtering. But I also did another approach that I think is less in line with that. And like I said, I did a lot of I did a lot more work on trying to figure out how to do this one. I actually started off with doing something that looks a little bit like this to try and like figure out how the data will kind of get like augmented and what models it might hit along the way. So it started off like it actually kind of started off looking pretty simple, and it was like helping to like organize my thoughts. And then I tried out some more approaches and it started to get really, really messy. This is kind of like the result of trying to figure out how to do the feature extraction or engineering and the what's it called? The dimensionality reduction for image data. I was yeah, it was interesting. I look forward to seeing how the feature engineering is done in this chapter. It should be interesting. I'm pretty happy with what I came up with. I decided to use auto encoders for dimensionality reduction. I haven't personally used those, but they should be pretty similar to PCA. And again, this is all the work I ended up doing was trying to figure out what all to do for the feature engineering and how to have it flowing through the system. There will be a normal looking diagram later in this video. This is the end flow of the transformations of the data. That's what this is kind of representing, is like how the data is getting transformed. I should probably explain this a bit better, is that each circle is kind of like one step of where the data is at a certain point in time, and then there's a transformation to the data. And this is how it's being transformed, what's being done to it. So for example, if a data model is making a classification of a data point, this is what it was before, this is the data going into the data model, and this is what the classification coming out of it is going to be, such as a convolutional neural network that's taking in a like simplified or what is it, like regularized image. It's run through an autoencoder, and then but it still has really high dimensionality, so it still is roughly an image, and then you stick it through that and you just get a tag out, or you could have a bunch of them, one CNN per tag. Anyways, this is the stuff I did trying to figure out how to do it. I'm gonna keep moving on. The requirements: user will provide an image file. Relevant image files will be returned to the user. Like I said, the feature extraction or feature engineering will be the spiciest part of this chapter. Otherwise, it's going to look very similar to, I think, what is it? Chapter 10, personalized newsfeed. Or there was another one. Oh, similar listings. Maybe it was chapter 9, similar listings. That was really familiar. Yeah. So that one is very similar. But this one is with images, which means you have to do a lot of it. So this chapter 2, is going to be basically chapter 9, but with some really spicy feature engineering because it's image data. Yeah, and then these are some other similar problems. I added some books to my list of resources. I took a class on data mining way back in college, and this was the textbook that we used in my class, and the material is really close to that. There's another one from a Stanford class called, wow, I spelled that wrong, called Mining of Massive Data Sets. You can access their material at mmds.org. That might actually end up going onto my book of my list of books tier list. Everything else is just Wikipedia, and then scikit-learn's documentation actually helps with learning machine learning in general. Okay, we can go back to our discussion. So I think I said it would probably be, that should be the word, item-based collaborative filtering. There could be a personalization step after the item-based collaborative filtering for personalization. Because if you're just doing item-based collaborative filtering, it's not going to have any personalization to it. There's no user context on it. But this problem is, it just seems like there's probably not going to be the user-based second step. I think some of the other problems do that later on in the book, but it's just about finding it's just visual search system. I think it's not going to rely on heavy user context. So I believe that's probably going to be missing. So dimensionality reduction is going to be really key here. That's why feature engineering is going to be such a challenge, is the dimensionality reduction is going to be really tricky. I'm more familiar with how to, I've done high dimensionality reduction before for text data. There's this really nice data set out there with like 22,000 routers articles. It's from like the news source Routers, REUTERS. And I've done that before, but I haven't done images because you can figure out any kind of semantic, what is it? Is the term latent semantic analysis. You can pretty easily figure out the topic of a news source based on the individual words, and you can like see the forest for the trees with articles with text. But with an image, you can't just look at one individual pixel and figure out what the image is of. And so that's why you have a more sophisticated data model with these, where you would need something like a convolutional neural network to recognize what it is an image of. Yeah, so that's the challenge here, is the like, you might need to do some like object recognition to add extra features as well. So you do dimensionality reduction, then also adding extra features. So I went into more detail about the dimensionality reduction stuff that you can do here. First, I'm going to resize it down to 100 by 100 pixels, I imagine. So whenever I've done a reverse image search, there's always just a bunch of different sizes of the exact same image that pop up. And so if you just resize it to a standard thing, you can even do some rounding on the colors. And then that will probably help with the data model for dimensionality reduction. When you reduce the amount of space that representing the thing in memory would take, it also reduces, it also would reduce the number of dimensions in this case. PCA is a thing I've used before for dimensionality reduction, but it was for text data. I don't think it's going to work that phenomenally with images. Autoencoders are an alternative that I heard of. There's also SVD. I've never used SVD. I've heard of somebody using autoencoders before, though. And yeah, it sounded interesting. I didn't personally use them. I've definitely seen somebody use them, and I think they're usually used in image context like this. And then another way is that you could possibly just do clustering over the data, and then you could use the cluster ID as a target class on a classifier. And so then you would have this, you would do clustering, and then you have the second classifier that can take a, you would do KNN to get a cluster ID, and then you would turn it back out into a list of IDs associated with that target cluster ID. But then you just have these like sets of images all tied together and they don't overlap. So that would not result in overlapping sets of images, which is the issue there. Yeah. And then I said you would probably want to recognize objects in the image. So for example, if you wanted to, if you gave it a picture of an apple and you wanted a bunch of other pictures of apples back, which is what I would expect instead of just a bunch of stuff that's red, some random red blobs, you would need to recognize that apple in the image. And so that is the second spicy part of the feature engineering. There's two challenges. I should just maybe pull that out as like a whole section. Challenges of just say feature engineering challenges for this problem. There's high dimensionality. Of course, I actually had a whole section on for the links. It's a really common term in college. My professor called it the curse of high dimensionality. This one just calls it high dimensionality, but it's an issue with when you have a lot of dimensions to your data. So high dimensionality, that's from the text too, but then there's also object recognition, which might be hidden latent analysis, or hidden latent semantic analysis. There's some kind of semantics you have to pull out of the image, some kind of hidden meaning that you need to be able to pull out, and you don't have anything like that with text data from what I've worked with before. In fact, with text data, you even do this thing where you remove the stop words, which is the stuff like the, a, for, stuff like that, and then you're just left with these meaningful words like economics or computer, and then you're able to like derive a topic from those words because they're highly correlated, highly associated with them. With a single pixel though, you can't really derive much meaning, so that's pretty huge here. So my approach, what I'm doing among these is resizing it down to 100 by 100, so it's a standard size. You might be familiar with those, the number recognition one, where it's they give you a 16 by 16 pixel image of a number, and it's either 0, 1, 2, 3, 4, 5, 6 through 9, and then you say what number it's. You train a classifier to say what number it is, and that one's very straightforward, and it's the standard size of the images that really helps it as well, but then it's also the very limited number of classes, which makes it simpler in a different manner than what I'm trying to accomplish with the pixel sizes. The standard pixel size, though, that will handle the variety of different sizes of the exact same image you would see on Google Images if you just pull everything down to 100 by 100. Auto encoders. So like I said, with cluster, the cluster thing, it would not result in overlapping sets of images, while auto encoders just finds a more compact encoding to represent it. The clustering approach I was talking about basically did an encoding down to like a single column, which is very bad. Oh no, I'm actually not going to be doing, I will be doing autoencoders. I will be doing autoencoders, but I don't understand autoencoders. We can go ahead and say that. It should be very similar to PCA, principal component analysis, and then CNN for objects like, so when I talk about tags with the convolutional neural network, it's like, is it a picture of an apple? Is there a dog in the picture? Is there a bridge in the picture? You can have multiple tags. Multiple tags is key. If it was just one tag in every single picture, then it would be, you could definitely do clustering. And that would get us there. I wouldn't have to do this autoencoder trick instead. All right, so for approach one, we're going to be dealing with images that are already indexed, already handled. So it's like if you just give it an image that it has already seen before, and you do your resizing and you do the autoencoding, and then you hash the output, the normalized output of that. If you do the hash on that and it's able to get found in this database as in it's seen it before at some higher resolution or something, you can just do a pre-existing item matrix DB, and you don't have to run any kind of point-wise point-wise ranking thing across all of them. It's you just already have, you've basically pre-computed stuff. You can have it pre-computed if you're just giving a thing it's seen before, you can just have it pre-computed for everything it's already seen before. And then you would just get something very similar to chapter 9, which was the similar listings on vacation rental platforms one. I definitely did this. I'm probably not going to go as deep in walking through this approach as I did with the chapter 9 solution. So if you wanted a more in-depth answer for this, you can head over there. I don't think this is what Alex is going to have in his book. He's probably going to have something a little bit more complex than this. I'd be surprised if this was all he had was just this like pre-computed thing like I'll show you. So I'll keep that one a little bit shorter. And I'll go into a lot more depth with approach 2. And then for making that though, you would have to do clustering. Bad options for clustering for your data model are agglomerative, hierarchical, because it scales poorly. It can't handle a massive amount of data very well. When you have, millions of images, and well, so it's, with millions of images, it's just gonna not be able to handle that scale of data points very well. And then dbScan does handle scale, but it cannot handle high dimensionality very well. And so that is one of the cases where the curse of high dimensionality is striking. Good options though, Birch, Cure, I think they're both density-based clustering algorithms, so those should probably be solid. I've heard they scale pretty well. I've used Birch before, actually. I've actually used Birch before. It was pretty solid. Yeah, I liked using that one. I haven't found anything that implements Cure though. I think Cure isn't really used as commonly. I've totally used Birch before. It definitely ran pretty fast. Distance measures. So when you're doing so particularly with like density clustering algorithms, you have to talk about the distance measures a bit. So a bad option is Minkowski distance. You're going to get an overflow, like an integer overflow. I actually tried it and I couldn't figure out why my clustering was doing so poorly until it hit me that like, oh, with 1,000 dimensions, I'm putting everything to the 1,000th power. And so then I'm going to get a overflow of my numbers, and it will just devolve all of my distance measures into pure noise. And then you're just going to be clustering over pure noise, and it's not going to have any meaning at all. A good option, possibly cosine similarity. That one seems okay. I'm gonna be doing that one. I'm gonna be using cosine similarity. Manhattan distance might work. Let's go ahead and say maybe. I haven't really looked into these ones as much for how they might work in this case, but there's Manhattan, there's Euclidean distance, so you square it with Euclidean distance, you square the differences and then sum them all up. I think it won't have that overflow issue. It should probably work fine. I'm somehow blanking on other distance measures. Yeah, but cosine similarity is what I'm feeling here. Okay, and then of course, approach 2, going to do a similarity comparison between each of the, between the input image that you're uploading. Right, okay. So this is talking about how, yeah, when you have that image and you're trying to do a nearest neighbors approach during runtime, it would have to do a pairwise ranking against every single record that you have. And so that would be big O of n against the entire database. And so then you want to do a candidate generation step first before you do the similarity comparison. So you should have a candidate generation step. And so I'm going to be doing something with candidate generation step and a similarity comparison, or a nearest neighbor approach with that. Yeah. Okay, I guess we can go ahead and hop into the diagram. Okay, we'll have the use case of a user that is trying to view similar images for similar images. And you'll have an image results service. So we're starting with approach 1, which is where it's an image hash, and we were saying that like they're not uploading a unique image, which should be most of the time. I don't think people usually will try and do a reverse image search on a picture that they actually had like just taken off their own phone or something. That is, I haven't really thought of like why anyone would really do that. So it should usually actually be pre-existing images, but then it wouldn't really be an exciting problem without talking about the case where it's not a pre-existing image that they're running against the service. So approach 1, pre-existing image. You will have an image results service. And you're going to give it an image file. And then you're going to return a list of relevant image IDs. And then you're going to go ahead and use a CDN for turning the image IDs into image files. So you're not going to directly send them all down there. That could be a bandwidth issue. Here we have an image file. I'm not doing it to the side to an S3 bucket or something. That might make sense. I think I've already added enough complexity to this problem, as you'll see later on, so I'm not going to worry about it passing through an S3 bucket or something. And we'll have an item store, similarly to chapter 9. So you have the image file, and then you're going to find this image hash code. Going to send it over to there. And then it should return a list of image IDs. And then the relevant image IDs are going to get passed over to the browser. Oh, I tried to type on the line. I didn't like that. Okay, and then you're going to turn those image IDs into actual image files with the CDNs that you don't have a bandwidth bottleneck on this service. Have that over here. And we're going to have the relevant image files. And then we need to talk about the schema of this database. So I've been doing this in other problems. I definitely want to do this here as well. So that I've got this model where the rows are image IDs and the columns also image IDs. And then the actual DB schema do it like this, where you have a image hash code, and then you map it to a list of image IDs. Or you can also, yeah, you can just leave it as a list because you don't necessarily need to index the second column. Yeah, this would work. Okay, and then let's talk about, yeah. So it doesn't have a data model in this one in the traditional sense. Approach 2 will have a data model for sure in the traditional sense of machine learning. But I'm still going to draw it just to kind of make sure everything's like super clear on this. I've really not liked that there's a lot of I mean, I still tried looking on the internet for some other sources that actually like try to tackle these problems, and usually I could not find anything that looked remotely like this, and it was very unhelpful. We're doing item, collaborative, filtering. We're just going to kind of get this thing through clustering. It's going to result in this data model. So and then I already talked about clustering over here, and we can just kind of do that. So a good option here, Birch and Cure for making it. I'm not going to go into the training, what is it called? Model training workers. I'm not going to go into the model training workers and the way that the data is collected or any of that. I'll go into that for approach 2. We're going to leave this approach as it is though, and we can go ahead and move on. So I'm going to copy and paste this, and we're going to move on to approach 2. Okay, so we have this image results service, and we're going to have a candidate generation step and also a ranking step like we've had in a lot of our other diagrams. And these 3 services could be merged together. That works perfectly fine as well. I have no idea what Alex is going to do, but that's just like a note, is that these 3 things could just be merged together. It doesn't really make any difference to me. But I think for the way when you're deploying, I think you would want to have, I would separate these out because I think for A/B testing purposes, it makes more sense to have be able to independently deploy the data model to these services. The data model clusters should be independently managed, so you can do A/B testing, and then also yeah, it just makes sense because of the way that you deploy data models. Okay, so you have the image file. You will want to extract features out of the image. So instead of turning it straight into a hash code, we're going to do some kind of the feature engineering transformation. Yeah, so we want to have feature extractor workers or task runner. So this, we're just going to do feature extractor. It's a task runner. It's only running for one data point, as opposed to when I say workers, usually when it's workers, it's doing transformation of a whole data set. And this one's not a whole data set. Have the image file. And then this thing is going to do a couple of things for us. It's going to resize the image. It's going to do auto encoder or dimensionality reduction after that. And then it's going to return feature vals for the image. It's going to return the image feature vals. So it's now in a language that our data models will be able to understand. Then we're going to send those image feature vals off to the candidate generation service. And so we have those, and we're going to have a data model on this one. And this one will be our convolutional neural network that identifies tags. So it takes in feature vals for an image, and then it converts it to, you could have a data model per tag. I think it's easier to train data models that only pick up on a single class at a time. You're going to need a target class per tag. Each tag is its own target class that you're going to try and predict properly. And so I think it is probably a lot easier to have a different data model for each one. And then you just like run it. You run the image feature vals against each of the trained CNNs per tagged. So we're going to say a tag, but you're going to get a list of tags. And then you're going to take that list of tags and you're going to run it against, we're going to have something, it's a little bit similar to what we had over here, but we're going to be using, a mapping from tags to image IDs instead. It is going to be we're going to use elastic search, and you're going to give it, you're going to be filtering down by that list of tags. Have image tags, and you will return list of image IDs. Okay, and you will return that list of image IDs. This is a convolutional neural network, which is a type of classifier. There's ways you can get neural networks to run in unsupervised learning, as in non-classification scenarios, but CNNs are usually feed forward in their classifiers. Then we want to pass the list of image IDs and the image feature vals over to the ranking service. We're going to do, we have at least this. And we're going to do pointwise ranking of the results, which means that we are also going to need to use the uploaded images feature vals. And these images, the list of images is going to be converted into their feature vals as well from a call to the image feature store. Just trying to make sure we're going to have enough room for what we're going to do in the future. Okay, so we have that. And now we're going to call the image feature store, which will convert each of those image IDs that it already has indexed and it's seen for a while and has gone through in offline processing. We have the image feature store. Trying to send that there. It's just the list of image IDs, or you could make a call separately for each individual image ID, and it'll return the list of their feature vals for each of them. So now they are in a format that the data model would be able to understand. So this one also has a data model of its own. I guess I didn't cover what I would use for the second step, but it is going to be you're going to need something that allows them to actually be comparable to each other. You are just comparing them directly to each other. You're just doing a pairwise ranking. That's right. Okay, so that's not even really a true data model. That one wasn't either. Yeah, it's not really a true data model because it's directly a database that you're pulling stuff back from. So it's not like how the CNN or like a trained random forest or GBM would look like, where it would be like a pickle file and you actually have it like hosted. And that one, it was like a database table. And over here, the data model is that you're going to do, you're just going to run cosine similarity. So it doesn't need to be like trained. You're not doing a trained thing to create a file. That's what I would consider a data model, is when you've like trained up this thing, you have to like store it in a file to like deploy somewhere. And so you don't have to deploy anything to get this thing to work. And we were just doing use cosine similarity metric to compare it to the uploaded image. And for the input, uploaded image feature vals. Let's center that plus candidate image feature vals. That is the input. And the output will be score for the candidate image. Just like that. Okay, we should talk about how this data model gets trained. I want to talk about that a little bit. Yeah, we'll extend this a little bit. We're going to have a model store. It's not going to be like under content-based filtering where you're like retrieving it with every request. You have to actually deploy it like it's a full like service deployment. It's like you deploy the data model alongside the executable or whatever, like the jar file that actually runs the service and handles requests. So just like you deploy your jar file running stuff on Jenkins, and that same Jenkins deployment, you also pull in the object from the model store that is the actual data model, which might be like a pickle file in Python. And it gets injected into the service kind of like a Java bean would. But in Python, it's a pickle file. So you're running deployment. This is something like Jenkins, for example. Fetch the pickle file. And you deploy your service along with the data model. And then, of course, you have to train up those data models. These have to come from somewhere. So I'm going to add the model training workers, and then we're going to stop there because the way that you get this training data is quite a story. And we are definitely going to cover it, but it's going to require a lot more stuff. So we're not going to cover that right away. Alex Shu's book is definitely not going to talk much about where this data is coming from. Okay, so that brings us to here. Next, I want to cover where we are getting the, I want to switch over to using regression instead of the cosine similarity metric. So say that for approach 2, candidate generation is CNN classifier outputting tags, locations, and then for the ranking, we're doing cosine similarity metric. Now we're going to move on to approach 3. I'm not happy with just leaving it as cosine similarity metrics. We're going to move on to a regression approach. And so now we'll actually have a trained model. Regressions are a supervised approach, similarly to neural networks, gradient boosting machines, KNN. You actually train a model and it's going to have to be deployed. So we're going to copy this and going to move it to over here. Now the data model is going to be a logistic or linear regression. Then you have a score for that candidate image. Okay. It's like a proper data model. And it's going to have to come from somewhere. Going to give ourselves some space. Nope. Okay, model, we'll have a model object store just like that. That will be getting deployed. We'll give it some space. Okay, and you're gonna have a model training worker again. then it's going to pull from the image feature store. That is going to be the not the target class data. And it's what are we targeting? Trying to target, oh, it was that I wanted engagement rate. Okay. So for this one, it's just similarity directly off of image properties. Ranking by similarity of image features directly to the loaded image. While here, it's going to be ranking by engagement. I want to add, do you want to show the images that they're most likely to click on? So the images might be a little bit less similar, but they are going to be the ones that get more clicks. So if you have a whole bunch of different apples, would you just show all the different resizings of it, like right at the top? Or do you also want to show a couple of different apples? Maybe you'll even show a green apple or something crazy like that in the top row of image search results. So you're increasing the click-through rate instead of just showing the most exactly similar as possible. So ranking by predicted probability user clicking the image, but it's non-personalized. We're going to, it's not going to be trained in a personalized manner. Come on. So that is the target class, is the click-through rate, engagement rate. So that is going to come from the data warehouse. It's going to pull it in from somewhere, and I am going to show exactly where it's going to get pulled in from. But when you're doing analytical stuff like that, the data should be living on, it should not be inside of a OLTP database that you're doing such a massive full table scan of. It's ETL. This is ETL. I should add that keyword on here, is that you're doing ETL. And so you shouldn't do that on an OLTP database. So we have the data warehouse. And then I want to use engagement rate from like the user. Like how often are they engaging with this picture? How often are they expected to? So we're going to have user clicking a thing on the page. And when they do that, it's going to somehow feed data to this user tracking service. So they click a thing, and then that data gets sent over to there, and it silently sends a 200 OK back, or it redirects them or something, but it's going to receive this, it's going to have this data from that interaction. When you're interacting on the page, their page is sending data. Come on. There we go. So we're going to use this interactions and engagements, interactions, and engagements EV is what we're going to call this. And it might go through a broker or something first, I don't know, but it's going to eventually do a write into there, return a 200 success back to wherever. Maybe it'll be through a broker intermediary, but you do an interaction, the data gets sent over and silently, and then it might feed it into a broker or something first, and then it gets response back and then gives you the 200 OK. But it's going to make it into that interactions and engagements database. And this is an OLTP database. You're not really going to be doing a whole lot with it. It's just basically getting a whole bunch of write operations. But again, if it's in if it's in prod, if it's handling online transactions, it should not be also getting used for gigantic analytical queries, which is why we want to do change data capture just with DB triggers. Seems like a fine way to do that. Yeah, and so it's going to get fed into the data warehouse, which is OLAP. Oh, this one is OLTP. Then you'll do an ETL job. You can go ahead and curve that. Be a little bit more clear about how that works. Request and response. And it also pulls in that. And then it does some training. And then it spits out a trained data model. It creates this trained like pickle file or whatever it is that it trains something in RAM, and then it has to serialize it to a file, perhaps a pickle file, and then paste it over into an object store for persisting and version control of that trained copy. Okay, so that is one point. We've got the linear regression now off of the click-through rate. I didn't label that it will be the training data. So that is the target class or column for training, for the training data. We didn't talk about where we're going to get our target class for convolutional neural network though. And that one is quite a story. I'm going to go ahead and copy and paste this one though, because you might not be following along quite as easily in this next step. And I'm definitely going beyond the normal scope that would be used for this problem. Yeah. I'm doing more of case studies than just plain old interview questions. I like to go a little bit deeper than traditional interviews will go. And so going from basically at the end of this second diagram, we were now going deeper than normal interviews after this one. This one is where you're getting to the point of a little bit deeper than normal interviews will go with these extra areas of where the data flow, how the data pipelines and the data flow works for getting everything from end to end. And this one's really going to go way beyond the scope of a normal interview for the end-to-end pipelines. Okay, so we've got, we're trying to make a convolutional neural network that given an image's feature values, given an image, you want to apply a tag to it. So that is going to come, so like where are these images coming from? You're displaying these images, like where are they coming from? They are coming from the web crawler. So like it's Google, like when they're crawling websites, they pick up on these images. And so we're going to show a couple of components from the web scraper that's used in our design for how google.com works. My video for that is just called web crawler. So we got our scrapers over here, got our external website. I'm not going to go super deep into all the pieces of web crawler, of course. We're going to keep that. And then I also had a component that I was calling the web pages object store, which is gigantic JS files or HTML files that are unflattened. And I imagine that the images will probably go in there too. So you have the scraper, it has this URL it needs to crawl. It pings it, sends a request there. Hey, show me the web page. Here you go. There's the web page. And then this thing persists it over there in the web page's object store. And then somewhere there's going to be this images object store, just the images on the internet that you're going to put onto the image reverse search part on Google Images. You're going to have this thing, you're collecting up these images from the internet, and you're looking at specifically just the images from the web pages you crawled, and you're going to be displaying them to users for reverse search. This part is where we did not pull that from the web crawler. This is where it's not really the web crawler. So for the model training worker, it needs labeled training data. So we're going to need to also have some training data at some point that's labeled with these tags that we want to train it with. That's the target class. So we need training data labeled with these tags, like an apple or a car or a bridge or I don't know, some dude's hat. Does that sound a little familiar to you guys? Have you ever had to click on some images of a bridge or of like an apple or something? There was a name for that. It's that's our next little use case we're going to cover, is that we have the browser for a user completing CAPTCHA. How are we getting our labeled data for the tagging thing for the CNN? Where are we getting these images that are already tagged with like the word apple or with bridge or with bus? Somebody's doing that work for us. Is Google paying contractors to do that? No, they're actually getting it done for free with CAPTCHA. And so we have these users that they receive these images, these unlabeled images, and they are clicking on the ones that have an apple in them, or a bus or a bridge, and then we are saving that. But we mix in some of the training data in order to check they're not a robot. We use some of our already trained data because this is a really hard problem for robots. Otherwise, we wouldn't need to have this gigantic setup, this complicated setup. If it was easy to do this, it's hard for robots to do that. And so we just give some of that training data in, and depending on how the users are labeling it, you can use off of your trained, some of your already labeled data to try and pick ones that are like not actually filling it out properly. But yeah, CAPTCHA, that's how we're getting our trained data. And so we are going to be pulling that into the model training worker. And the model training worker should be using the same type of the feature data, the non what's it called? Non-target columns, the columns that are not part of the target predicting class, the class we're trying to predict. That should be the same stuff that we're using for our feature store for the images. And so with the image feature store, let me move this over. With the image feature store, it should actually be the same data as the training data that's already labeled. So that should actually be a copy. So I'm going to label that with same data. And I think it would probably be CDC from OLAP over to this. So this one is OLTP. And this one should be, well, I mean, you would have the user responses, and then you're going to turn that into training data. I think I went into more detail about this in one of my other videos. It might have been the Google Street View blurring system for chapter 3. Yeah, that one had a little bit more. I also went into a little bit of depth on CAPTCHA in that one. This one should be a solid line because it's not, that's pretty much exactly what's going on. Okay. And then we're going to label our two different components here to, actually, let's use that. So this is a simplified view of the web crawler over here. And we also have a simplified view of CAPTCHA over here. And I just want to make that very spelled out for everyone. That's where we're getting those images that we're showing to everyone. And then how are we having them already labeled? It's from over here in CAPTCHA, simplified view of CAPTCHA. The unlabeled data, the raw images themselves, the labels for the images over here. That is where we get this model training data, the data for training our convolutional neural network over here. Let's zoom out while I try to remember if there's anything else I wanted to do in this video. Okay, there's our whole diagram for the training data for the CNN. Oh, I didn't label the image feature store with the little box that I've been trying to do for every problem. So I need to do that. And we're going to make it solid lines. And here, the rows are images. Image IDs. So you're going to be mapping image IDs to image features. So the normalized or regularized features. Let's maybe spell that out. So mapping of ID to normalized. It's how the image looks after running it through an autoencoder and adding in the tags. Say host autoencoder. Sure, good enough. There's our table for the image feature store, which is immediately to the left of our new box. I have everything now. Yeah, I think I've covered everything that I want. Awesome. Yeah, all right, I can let you guys go. Thanks for watching. I really appreciate it. You guys have a wonderful day. Thank you. Bye.